Hello guys, we are going to see more and more derivatives of functions. In this video, the objectives are the following. We are going to review the sum rule, the product rule, constant multiple rule, and other rules that are applied when calculating derivatives. We will see some examples, and as usual, be careful because some ideas of calculus and algebra are needed. Also, we are going to talk about the limits, and this should be known at least, a little bit at least, okay? So, we are trying to calculate derivatives. Here, you have the most important properties when calculating derivatives. I guess you know the basic derivatives. At least you have in your mind a basic list of functions and their derivatives, okay? If not, I will recommend look for any textbook, a list of derivatives without chain rule, because here you are going to see the chain rule, and remember them, because it's important. I don't like memorizing anything. I prefer just to obtain the formulas if needed, but this takes time, and also a big quantity of knowledge. But remember, in this case, my advice is always to remember this list of derivatives. Let's go to talk about these properties. Okay, the first property, let's suppose you have two functions, real functions. Sorry guys. And what we are going to do is to calculate the derivative of the sum of these two functions. Anytime you see something like this, you calculate the derivative of the first term plus the derivative of the second term, as you can see here. Okay, so adding function, or by the way, subtracting functions, there is no problem with derivatives. You just calculate the derivative of one function and the derivative of the second function. Okay, what is happening with the product? Is the same. Be careful, guys. Be really careful. This is very important. It's something we tend to do, all of us, and it's completely wrong. Okay? It's the difference between knowing something in mathematics and not knowing anything. Okay. The product is not the derivative of the first one times the derivative of the second one. That is what you want to do, but don't do it. Okay? The derivative of the product has a rule, and the rule is the derivative of the first function times the second function without derivative, plus the first function, as it is, no derivative, times the derivative of the second function, the derivative of g. Okay? This is the rule you need to apply anytime you need to calculate the derivative of a product. Okay? Be careful. Again, it's very tempting to just put the derivative of the first one times the derivative of the second one. That is completely wrong. Okay? Also, another property, very important. If I have a function multiplied by any number, any constant, then the constant remains exactly the same. Imagine that I have 3 times x squared. Okay? For example, 3 multiplies x squared. 3 remains the same. Don't touch it. Okay? Because it's multiplying the function. Then the derivative of x squared is 2 times x. Okay, 2 goes down, perfect. So the final result is going to be 6 times x. Okay, but 3 remains the same. So the idea of the third property is that constants that multiply the function remains the same. Don't disappear. Why I'm telling you this? Because normally when you see a constant, you think, okay, the derivative of a constant is 0. Okay, if this constant is alone. Okay, if it is multiplying a function, don't touch it. Leave it this way. Leave it that way. Okay, so another example. 2 times the exponential function of x. All of you know, you should, that the derivative of e to the x is e to the x. So if I multiply by 2, then the derivative is 2 times e to the x, because 2 remains, is multiplying the function. Another important rule, the quotient rule. It's very similar to the product rule, but is when we have a quotient of functions. Okay? In this case, it's a little bit more complicated. I think it's the most complicated of all these properties. The idea is that you need to, in order to calculate the derivative of a quotient, is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator divided by the denominator squared. It's important. I guess all of you have practiced this before, but if not, take your time to get used to these properties, okay? If you have any doubt, you have my email at the beginning of this video, okay? So just write an email and I will try to answer as fast as possible, okay? So this is the rule of the quotient. Again, it's very tempting to just, when you have a quotient, to calculate the derivative of the numerator and the derivative of the denominator. That, by the way, it's what you do when you are solving or you are applying L'Hopital's rule, okay? But this is not the case. I'm just trying to calculate the derivative of a quotient, and the rule is that. And finally, if you have two functions composed, then the derivative is the derivative of the external function at the initial function g times the derivative of what is inside. Okay, when you have a composition of functions like this, then it's f prime of gx times the derivative of the function inside. This is the most complicated, no, it's not the most complicated rule or property, but it's one that you are going to apply many, many times, and we will see examples of that. Okay, so let's start with an easy example. Okay, let's start smooth. Okay, I wrote here a polynomial degree 4. Perfect. What is the derivative of this polynomial? As you can see, you have the solution here, but just okay, let's see slowly. The derivative of x to the 4th power is 4 goes down and I subtract 1 to the exponent. Okay, so it's going to be 4 times x cubed. The same happens here. Negative 2 is a constant, so negative 2 is multiplying, so please write it exactly as it is. The derivative of x cubed is the same property. 3 goes down and I subtract 1 to the exponent. So it's going to be 3x squared. But 3 multiplies 2, it's the reason we put here 6. The derivative of 3x, the derivative of x is 1. 3 remains, perfect. And finally, a constant that is alone, is not multiplying any function. The derivative of negative 2, 0. So I didn't write it here. Can we calculate the second derivative? Yes, of course. We take the first derivative and calculate the derivative again. 3 goes down, 3 times 4 is 12, and I subtract 1 to the exponent. The derivative of negative 6x squared, the 2 goes down, so this is the reason I wrote negative 12, and I subtract 1 to the exponent, so it's just x. 3 is a constant, alone, disappears. Next derivative, third derivative, let's keep going. In the first part, the 2 goes down, 12 times 2 is 24, and I subtract 1 to the exponent, 24x. Negative 12x, the derivative of x is 1, so it's there's only remaining a negative 12. Next derivative, okay, the derivative of x is 1, so I got this 24 in here, and negative 12 disappears because it's a constant. Next derivative is just 0. The fifth derivative is 0. The sixth derivative is 0. And from this point, forever and ever, the derivatives are going to be 0. Okay? So we started with a polynomial of degree 4, and its derivative reduces the order at one degree at a time. Okay? Another property. Okay. Chain rule. BIT. Very important thing, guys. So we have the logarithm of the cosine of this quotient. Okay? 3 functions in a row. Logarithm, cosine, and this function. Be careful because it's logarithm at something, cosine at something. What I'm trying to tell you is that logarithm and cosine are not separated. It's logarithm of cosine of x squared plus 1 divided by 3x. Okay, what is the derivative of that? First, we calculate the derivative of the logarithm. The derivative of the logarithm, by the way, is 1 over the function that is inside. So, as you can see here, is 1 over, and I write everything between parentheses on the denominator. Perfect. This is the first part. Now, we need to calculate, we just calculated the derivative of the logarithm. Let's calculate the derivative of the cosine. What is the derivative of cosine? Minus sign, or negative sign. So that is the reason I write this here. Negative sign, and you leave whatever is in parentheses exactly the same. Times, sorry, this prime shouldn't be there, okay? This is a mistake. I already calculated the derivative of sine. And now what I'm doing is calculate, and the final point is calculating the derivative of this quotient. Sorry, it's like going one function at a time. Okay? First we calculated the logarithm, then we calculated the cosine is negative sign, and finally we calculated the derivative of whatever is inside. I just indicated here the derivative of that. This is a quotient. This is the derivative of the numerator times the derivative of the denominator minus the numerator times the derivative of the denominator divided by 3x squared. Okay, and now, once you have this, you need to simplify. Simplification is not so difficult. You only need to expand this expression. Sine over cosine is the tangent, if you want. If you are not so sure, just leave it at this stage. But it's a pity if you just don't simplify and make it shorter, okay? But the main idea I want you to remember from here is that when we have a function of a function of a function, you only need to calculate derivative and derivative and derivative of the three functions one at a time. And please recall or remember that this function is left exactly as it was at the beginning until the last step in which you calculate the derivative of this function. Okay? This is complicated somehow, but you need to get used to this. Okay? If you don't understand, please review exercises because this is very important. It's a very important part of derivatives. Okay, finally, if f is differentiable at a given point, then we can just plot the tangential, plot. Of course we can plot, we can just calculate the tangent line. And the formula of this tangent line is this expression. This is the function given from the beginning at the point you want to calculate the tangent line, the derivative. Remember that the derivative at a given point gives you the slope, okay, of the tangent line. So that is the reason it's written here. So the derivative of the function at this given point times x minus a, okay? If you want the representation, here you have this is the function x cubed, if I'm not, cubic polynomial, and the tangent line is this one. Why I plot this tangent line that crosses the function? Because we normally think that the tangent line never crosses the function, and it can happen like you see in here. Okay, and finally, in order to finish this video, I want to recall three important theorems. The first one says that if the derivative is positive, then the function is increasing. If the derivative is negative, the function is decreasing. I need to go back 1 second. If f has a local minimum or maximum at a given point, then the derivative is going to be 0. This has to do is related with the tangent line. If it has a maximum, the tangent line at the middle point, at the point that is the maximum, is going to be 0. Okay? And finally, if the second derivative is positive, we say that the function is convex, and if the second derivative is negative, is concave. So, guys, what have we seen in this video? We just reviewed some derivation rules, and we have seen some examples of these derivatives. I hope you find this helpful, and thank you for your attention.